Hello everyone, today my team and I are going to talk about convolutional neural networks.
So what is a CNN? At its core, a CNN is a type of neural network specifically designed to process grid-like data, such as images or videos. What makes CNNs unique is that they are inspired by how our brains process visual information. Just as our eyes and brain detect shapes, edges, and textures to identify objects, CNNs break down an image into smaller parts to analyze and understand its content. CNNs operate in three main steps. First, the convolution layer applies small filters to the image to extract features like edges or textures. Next comes the pooling layer, which reduces the size of the image while preserving the most important features. This step makes CNNs more efficient. Finally, in the fully connected layer, these extracted features are combined to make predictions, such as classifying an image as a cat or a dog. So why CNN for images? Images are incredibly complex data. Each pixel in an image acts as a feature, and a single image can have thousands or even millions of pixels. If we try to process all this raw data directly, it would be computationally overwhelming. CNNs address this challenge by focusing on patterns, such as the edges or textures, instead of analyzing every single pixel independently. This makes CNNs extremely efficient for tasks like image recognition. One of the key strengths of CNNs is their ability to automatically extract features from data, unlike traditional methods, where features had to be manually defined. CNNs learn directly from the data. They also excel at identifying spatial patterns, progressing from simple features like edges to more complex shapes and objects. This scalability makes CNNs suitable for tackling highly complex tasks. So far, we've explored how CNNs work, but what makes them truly exciting is their impact on the real world. CNNs are at the heart of innovations in industries like healthcare, security, and transportation.
So, as anticipated, CNNs find applications across many different fields. We will now go through some of the most interesting ones. And we will start with a problem that I actually come across a lot personally while studying. Now, believe it or not, in the first picture, it's my handwriting. And yes, even I have issues reading it. Imagine the embarrassment for me when people ask me for my notes and I cannot even tell them what I wrote. Well, luckily, CNN can do that for me. Handwriting recognition was actually one of the first applications of CNNs. In the late 80s, in fact, CNN was employed as a handwritten zip code recognition system that would help streamline mail sorting, making the process more efficient for postal services. CNNs are not only useful for analyzing handwriting. Today we see CNN applications in our everyday lives, starting with our phones. CNN can distinguish features of our faces to verify our identity and recognize us even when, I don't know, we're wearing glasses or we're not looking at our best. So every day we're asked to show our faces for facial recognition in order to unlock our phones or authenticate access to specific applications. Another fun application of CNNs can be found in social media. By detecting the face characteristics and identifying specific points in our face, CNNs enable the application of our favorite filter, allowing for the correct positioning on the screen. The ability of CNNs to detect and recognize objects has been employed most recently in car safety, and it's at the foundation of advancements in autonomous vehicles, helping to understand the environment in which the car is driving. Finally, one of the major breakthroughs of CNNs is in medical treatment, assisting doctors in making a diagnosis based on medical imaging, for instance, X-rays or MRIs. And it is within this field that Jerome will illustrate an implementation of the model.
Hi everyone. Today I'm going to walk you through the process of applying convolutional neural networks to a brain tumor detection project using Python. I will also explain how we visualize the model's performance through graphs showing accuracy and loss over training epoch. We will dive into the process by covering 7 essential steps. These are setup and dataset, data preprocessing, building the CNN model, compiling the model, training the model, visualizing the results, and model evaluation. The first step in any machine learning project is to import the necessary libraries and load the dataset. In our case, we're using a dataset from Kaggle called Brain MRI Images for brain tumor detection. We started by importing essential libraries like TensorFlow, Keras, and Matplotlib. TensorFlow and Keras are used for building and training our CNN model, while Matplotlib helps us visualize the training process. We use Kaggle's API to download the dataset. After downloading, we extracted the files into a specific directory. The dataset contains two main folders, one for images of brains with tumor labeled yes, and one for images without tumors labeled no. Furthermore, our total observation consisted of 203 images for training and 50 images for validation. Before training the model, we need to pre-process the data. This typically involves resizing the images, normalizing pixels values, and splitting them into training and validation sets. We resize all images to a uniform size, typically 150 by 150 pixels, which makes it easier for the CNN to process them. Images are normalized by scaling the pixel values between 0 and 1. This helps the model train more efficiently and speeds up the process. To prevent overfitting and make our model more generalizable, we use data augmentation techniques. This means creating slightly altered copies of the images. Next, we define the CNN model itself. As my colleagues already explained in previous section, a CNN is a deep learning model that's specifically designed for image processing. It works by using multiple layers to automatically extract features from the images. Here's a breakdown of the layers in our model. The first few layers are convolutional layers which apply filter to the images to detect basic features like edges, textures, or colors. These features are learned during training. After each convolutional layer, we apply a pooling layer to reduce the spatial dimension of the image and make the computation more efficient. Once the convolutional and pooling layers have extracted features, we flatten the data into a 1D vector to connect it to fully connected layers. These layers help the model learn complex combinations of the feature to make the final classification decision. The final layer has a single neuron with a sigmoid activation function, as we are dealing with a binary classification problem, meaning yes if the image has a tumor and no if the image doesn't have a tumor. After defining the model, we compile it using an appropriate optimizer and loss function. We use the Adam optimizer, which adapts the learning rate during training to improve performance. Since we are performing binary classification, we use binary cross entropy as the loss function. Lastly, we use accuracy as the evaluation metric, which measures how often the model's predictions are correct. We then train the model on our training data using the fit method. The model will learn to identify patterns in the MRI images by adjusting the weights of the filters in the convolutional layers. We set the numbers of epochs to 10, which means the model will go through the entire training dataset 10 times. During training, we also validate the model on a separate validation set to track its performance on a data it hasn't seen before. After training the model, we analyze its performance by plotting the accuracy and loss graphs over the training epochs. These graphs help us understand how well the model is learning and if it's overfitting. The accuracy graph shows how the model's accuracy improves over time. Ideally, we want the accuracy to increase with each epoch, indicating that the model is learning to classify the images correctly. For example, in our case, the training accuracy increases over the epochs, showing that the model is learning from the data. In the last epoch, the training accuracy is 89.19%. The accuracy of the model is improving steadily, indicating that it is correctly classifying more images as the training progresses. The loss graph shows how the model's loss decreases over time. The loss represents how far of the model's predictions are from the actual values, so lower loss values indicate better performances. In our model, we see that the loss decreases as training progresses from 3.62 in the first epoch to 0.29 in the last epoch, which indicates the model is getting better at making predictions. Similarly, the validation loss also decreases as the epochs progress from 0.456 in the first epoch to 0.47 in the last epoch. This indicates that the model is improving in terms of how well it predicts the validation data. Finally, after training, we evaluated the model on the validation data to check how well it performs on unseen data. The validation accuracy and loss tell us how well the model is likely to perform in a real-world scenario. In our case, the model achieved around 80% accuracy on a validation set. The validation accuracy of 80% means the model is able to correctly predict whether an MRI can show a tumor or not 80% of the time.